Hello, everyone, and welcome to today's Semi-EDA standards are essential for smart manufacturing, what you need to know and why. Before we get started, I'd like to go over a few items so you know how to participate in today's event. You've joined the presentation listening using your computer speaker system by default. If you prefer to join over the telephone, just select phone in the audio pane and the dial-in information will be displayed. You will have the opportunity to submit text questions to today's presenters by typing those into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. Today's webinar is being recorded and you'll receive a follow-up email within 24 to 48 hours with a link to view the recording. I'd now like to introduce your presenter for today's webinar, Alan Weber.
Yes, good morning or afternoon, depending on where you're logging in from. It's a real pleasure to have you online today. This is a topic I think that's important to the industry, and we appreciate your interest and questions. We look forward to addressing those during the end of this session today. All right, as Cheyenne said, today's topic is Semi-EDA standards essential for smart manufacturing, what you need to know and why. This is the first of a two-part webinar. Next week at this same time, we'll be covering topics on the implementation side, so the how of the EDA standard. So today is the what and the why. Here's some obligatory legal information. We'll move on past that. And today's agenda will start with a quick background of the EDA standards, where they came from. For those of you in the design world, EDA does not mean electronic design automation. In this context, it means equipment data acquisition. So please keep that in mind. Jack Downey will then cover their experience and insights from their implementation. They were the earliest adopter of these standards well over 10 years ago, and have been very nice to share that some of those insights. I'll then go into specific applications that can leverage the EDA standards, the manufacturing benefits that result, and the requirements that are implied by that that should go into your purchase specs. And then I'll quickly cover the preview of next week's session so you'll see what to expect and leave some time for Q&A. All right, our objectives today are to provide you a basic understanding of a list of EDA related topics. In the hour that we have, there's no way we can make you an expert on any of these things. But our goal is to make sure that you feel like this is one of the best hours that you could have spent this week. So we'll talk a little bit about the EDA capabilities and concepts, how they're differentiated from the SexGem and GEM 300 standards. Again, it should be clear that EDA is not a replacement for any of those. It complements the command and control functions of GEM. Jack will share some of the key insights from their experience. Then I'll talk about manufacturing applications and benefits, make it clear that there are a number of stakeholders that can be positively affected by the data collection capabilities of the EDA standards, but you don't get that without some revision of your purchasing specification. So I'll talk about that and that process, and then share a little bit about the adoption status across the industry. A lot of my job in the last 5 years has actually been promoting the adoption and use of these standards. And again, it's a privilege to have you online to learn all about this. So the final goal is to leave you hungry for more information, because again, you won't be an expert on any of these topics after an hour. All right, a little bit on the background. The EDA standards actually began their definition almost 20 years, in fact, exactly 20 years ago. Factories needed a more flexible approach for collecting and distributing, high-density, real-time equipment and process data. At the time, fault detection algorithms were moving from just lot-level post-process to actually within process and sometimes even within wafer diagnosis, and then interdicting the tool if it looked like it was drifting from its operating envelope. And so we needed a better way of collecting data to support those algorithms. And run-to-run control applications were moving from lot to wafer and even site level. So we needed better data collection to support that. In that era, there were a number of potential systems being offered by the major equipment suppliers, but they depended on custom interfaces and vendor-specific architectures. And so the end result might have been a whole collection of proprietary applications rather than a standards-based approach. So that was a serious motivation as well. And so EDA provided a way of supporting those kind of applications with a standards-based approach in a multi-client architecture. From a performance standpoint, there were also expectations beyond what GEM typically supports. The 1 Hertz data collection was seen as insufficient for those kind of algorithms. It was fine for sort of recipe level substrate movement and OEE and lot level control, but not for the kind of applications that were emerging at the time. So 10 Hertz frequency at the sort of recipe step boundaries was becoming a key requirement, and even faster for rapidly changing parameters, plus better ways of actually narrowing in on the specific events for high frequency data collection were needed. The final requirement, of course, was being able to change your data collection requirements, as and when they came up, rather than having them be locked down and under revision control. And so they needed a way that process engineers and industrial and equipment engineers could actually modify their requirements on the fly without the direct support of the IT folks. And this was realized in these standards. Okay, a couple of words about how they fit together. EDA standards are a suite. It's not just a single SIMI-E number. There are 3 of the standards that deal with the equipment model. That's the E120, 125, and 164. They're all concerned with the structure and content and access of the equipment metadata. You'll notice in this diagram that information actually resides on the tool side, not on the factory side. And we'll get into the implications of that later. The first standard that you have to use, though, to access the EDA interface for equipment is E132, and this is the security standard that allows you to authenticate and authorize access to the equipment. All communications within an EDA context are done within a session, and so you have to be an authenticated user to establish a session. From then on, all the communication back and forth happens within that session. Now, this ladder diagram shows a 1 client and 1 equipment, a client being a factory application. In actuality, you can have multiple clients for a piece of equipment and multiple equipments talking to a specific client. So it's really an end-to-end connection here architecturally, but for simplicity, we're just showing 1 client talking to 1 unit of equipment. So once a session is established, the very first thing that the client can do is request that the metadata from the tool be sent over. And that's a set of messages that respond with all the components descriptions in the equipment. Once you have that information, then you realize what is available to be collected, what events you can monitor, what parameters you can collect, what exceptions or alarms to expect. So given that information, you can then fashion on the client side a data collection plan, which is the explicit definition of your requirements for data collection, what data you want under what conditions. Now, the data collection plans are actually stored on the equipment. That's another key aspect of this. So you don't have to poll the equipment for information. You define and store a data collection plan and then activate that on the tool. The tool is then responsible for monitoring the conditions under which you wanted different kind of data and providing reports with that data when those conditions are satisfied. So once a DCP or data collection plan is activated, then the tool monitors the conditions, provides reports as those conditions are fulfilled, and you capture those on the client side until, of course, that DCP is deactivated or the session is closed. So this shows how the pieces fit together. All right, from going a level deeper, the E120 standard talks about the static structure of equipment, and it's a hierarchical description based on 6 or 7 node types, 4 of which you see in this in the picture on the left. Any of those nodes can then be decorated with all sorts of additional information about the state machines and events, semi-objects, parameters, exceptions, all the other things that describe the behavior of that equipment. And E125 also defines the services by which you request that information to be sent. After about 5 years of direct experience with these models, the early adopters said, we need more guidelines on how these models should be constructed, and that resulted in the E164 standard, which is the EDA common metadata. This standard specifies the naming conventions for nodes and parameters. It specifies how they should be structured and grouped. It actually gets into specifics about what should and should not be included. And the benefit of this, of course, is that over time, as equipment suppliers adopt this, you'll end up with a lot of consistency of the implementation of common parts of the equipment, the parts that are non-process specific, so that you know exactly what to expect when looking at a metadata model. What you see on the right is a tree view of a typical metadata model, and you can see where process modules and parameters and gate valves and other pieces are. You'll notice there's a couple of pieces in there that are not actually hardware. There's an EPT tracker, which stands for performance tracker. What you can't see on that page is a material manager and a job manager. These are components of the model that actually deal with logical elements that come and go, like jobs and substrates. So in addition to the fixed parts of the equipment, the pieces that come and go are also represented in that model. And E164 provides a lot of consistency over time. Okay, the final key concept in the standard, of course, is the data collection plan. This data structure is what a DCP looks like, and you can see that the data collection plan can have 0 or many of 3 different data request types. An event request, which is triggered by the occurrence of an event, and then a set of parameters is provided. A trace request, which is something you activate and deactivate with start and stop triggers, which can have multiple conditions in there. This trace request provides a set of parameters at a given real-time interval, anywhere from multiple seconds down to hundredths of a second, and then that continues until a collection count is reached or the stop trigger is reached. The final kind of request is an exception request, and this is analogous to the gem alarms. And you can blend multiple of these request types within a data collection plan, and the reports that the tool generates will be structured similarly from these request types. So that's the final key element of EDA is this DCP. Okay, so let's start here now with a poll question. These standards are quite complex and quite voluminous, actually. And the question is, do you actually have access to the text of these semi-standards within your company? Of course, if you don't, they're available from the SEMI website for purchase. They are licensed material, but they're well worth the price. And if you want supplemental information about how they actually work, we have a great deal of educational data on our website. And so either place you can find information about the SEMI standards. We'll give you all some time to look at this. Again, the SEMI standards are quite detailed, and the hope is that nobody should have to go into every bit of it, because there are commercial solutions for both the equipment and the factory side that enable you to implement those without having to read every word of them. Okay, it looks like we've got sort of 70% of our attendees responding. Let's kind of see what the results are. Yes, well, we got a third of the folks are not quite sure, 40% are yes, and 31% no. So, all right, for you, so you 31 and 30%, again, you can go to the SEMI website and see, where they are. There's a piece of software called SEMI Views that actually allows you access to all SEMI standards from either a reading or writing, reading and replicating standpoint. But we've got a lot of information on our website about that as well. Okay, let's shift gears now. Let's see, do I need to click again? There we go. Okay, as I said earlier, but I want to remake this point, EDA does not replace GEM and GEM 300. It is a complement to GEM and GEM 300. It's intended for high-speed, high-density data collection, but does not actually write any information to the tool. So things like interdiction of a fault or adjustment of a recipe parameter in a run-to-run control environment, or changing equipment constants or configuration parameters, those sort of things have to be done with GEM or GEM 300, not EDA. And again, the differences are EDA uses common sort of web and internet technologies for its communications, whereas GEM is a binary protocol, but they both share TCP/IP as an underlying technology. Again, GEM is for command and control, whereas EDA is for data collection. GEM doesn't have any explicit way of getting the data, except there are GEM commands for requesting the list of SVIDs and event IDs, but it's not as well structured and self-documenting as metadata in EDA. The actual implementation of GEM in most scenarios is a point-to-point implementation, so you can only have one client connecting to a GEM tool. Whereas EDA architecturally by design supports multiple clients. Some implementations of GEM, in particular ours, do support multiple connections, but that's not actually typical. EDA is mostly adopted in 300 millimeter fabs. It's not an easy thing to retrofit on an existing tool, and so it's mostly in the 300 millimeter world. They do have similar sort of data collection capabilities, but EDA has intended to have far higher granularity in the information available and higher performance. And it also has far more capability for triggering. Okay, let's now shift gears to Global Foundries. Unfortunately, Jack Downey called me right before we were scheduled to do our coordination connection. He has a factory issue that he had to give his attention to. He may join us hopefully later in this hour, but he could not actually commit. So I'm going to skip through his 5 or 6 slides and hope he joins us later. If he's not able to, I'll cover a couple of them, but he sent his sincere apologies to the group. He's a production guy, and when production problems happen, he has to be there. So that's where we are. Jack is a longtime colleague and committed early adopter of the EDA standards, and he had some good data to share with you, and he'll hopefully be able to do that later on. Perhaps he could join us next week if he's not able to join today. So my apologies as well. All right, let's move past these into applications and benefits. Again, we won't be able to make you an expert on any of these things in an hour, but here's a list of some of the applications that have, in the production setting, specifically leveraged the capabilities of EDA, whether it's the details in the model or the higher performance data collection or the very fine-grained data framing you can do with conditional triggers. But the key of this list here is that it's not just process engineers that are impacted by these standards. Throughput monitoring is typically the domain of an industrial engineer or an equipment engineer. Of course, FTC are where the process and the statistics folks get involved. Product time measurement is actually a new application based on a fairly recent semi-standard that gets at where wafers and lots spend all of their time. For processes that for which exposure to atmospheric conditions can be a problem for oxidation, using EDA to support a very precise lot completion estimation is one application. Of course, fleet matching and management based on fingerprinting of the underlying control mechanisms is another application. An equipment engineering application, and the facilities people also are interested in subfab data and facilities data. So there are ways of using sort of edge devices and gateways to support that use case. Of course, specialty sensor access and log file processing, these are sort of out of the mainstream of normal data collection and normal interfaces, but there are clever ways of using the EDA standards to accomplish those. And then finally, machine learning and AI application support. These technologies depend on lots of good data, which is what EDA was intended to address. So I'm going to cover a handful of these in a little more detail, with sort of a standard profile to give you an idea of what how they're structured and how they leverage the standards. So let me go through that. The first one we'll talk about is throughput monitoring. This is one that's sort of intuitive. Watching a tool to see how fast it's processing material is something we regularly do, but doing it at the level of individual wafer movements and recipe step executions can be key to catching what I'll call productivity excursions quickly. So it's especially important to monitor the real-time throughput of bottleneck equipment, because if you lose productivity on these equipment, you never get it back, because the bottleneck tools dictate the actual rate of output of a factory. So watching these to make sure it's not drifting away from normal productivity is key. Now, normal depends not just on the tool, but it depends on the recipe and the layer that you may be working on. So there's some bookkeeping that has to go on to make sure that you know what normal is under all those conditions. So the solution components of this application would be a way of monitoring the material movement and recipe execution events, and then calculating the effective process time for that combination sort of on the fly, and then comparing that to the expected average. Of course, the context data, which is what lot, what product type, what process am I running, this is the information you need to actually know that you're comparing apples and apples, the equivalence classes of the runs, and then can flag the outliers. Now, the way EDA is leveraged is it has access to all of the material movement events, not just the start and stop of a FOUP, but down into the individual movement of wafers within components of the equipment, as well as the recipe execution, start and stop, and the recipe step change events. And at each one of these events, EDA requires that the sufficient context information be available to be able to do that bookkeeping. Now, with this kind of granularity and visibility, you can watch the tool's effective cycle time, catch productivity excursions much more quickly. MTDD here stands for mean time to detect, and improve the effective throughput performance by, let's say, 3 to 5%. Now, the way to look at this, and this is, I'll go into more detail on this one than others. If you're familiar with the E157 standard, which is the process execution tracking standard, it has events that chronicle the start and stop of a recipe, and you can see that's the execution started and stopped, event transitions number 2 and 3 on the left there. But they also have events that tell you when the recipe step changes, and that's what these events transitions 5 and 6 are. And by monitoring those events, you can actually see, look for differences in different recipe executions, depending on, if you have some that are, let's say, dictated by an endpoint detector rather than just a fixed time. If you look at the representation of that state machine in an EDA tree, you'll see the E157 state machine. You'll see the 7 events that constitute that machine listed here. And the 4 that I've got circled have got red arrows next to them. And if you were to click on the little plus sign there, with each of those events, you have a list of context parameters that are available at every firing of that event. And so you see, you can tell, which module am I in, which process job am I running, what recipe am I running, and what step within that recipe am I on. This is the information that you need to properly account for that that piece of time and add it into the expected execution time. So given that information, you can generate all sorts of reports and displays about what happens, whether it's one of these tunnel displays of a kind of a golden trace through the different recipe steps, or if it's a multi-lot Gantt chart of where, let's say, each wafer spent its time. These you can see in this one there's kind of a stagger. This is actually a litho track and a scanner combination that had some unnecessary delays in the middle that were discoverable by watching some of the internal events. So that's how you sort of go from the statement of a problem to the semi-standards to the specific events to the data that you need to figure out what's going on. Okay, let's talk about a couple of others. FDC, of course, is the first and heaviest consumer of most EDA implementations in the factories. And the key in FDC, of course, is to apply these multivariate statistics to catch process excursions as quickly and reliably as possible while still minimizing false alarms. And the way that you do that, of course, is you want to be collecting data at the right rate, at the right moment in time within a recipe to populate, well, to first of all, develop these statistical models, and then to evaluate them in real time. The two solution components there, of course, are the multivariate analysis tools, which take all this data, and then the context evaluation that you need to group models into equivalent classes, which some people call threads of execution. The piece of EDA that is especially useful here is what's called the conditional trigger. And in the Freeze 2 implementation, which is the sort of second wave of EDA implementations, there is a way of actually triggering not just on an event, but on a set of conditions, inequalities or equalities of other parameters based on that were true at that event. So you can use parameter thresholds, you can use specific recipe step numbers to do different data collection at a different rate, depending on the critical process area. So in the little diagram at the bottom, you see there's a transition phases where you may have overshoot and undershoot. You'll probably be sampling that window faster than the steady state window, and all that is very easy to do with the EDA standards. So the ROI factors, of course, are fewer excursions, lower false alarm rate, catching those excursions that do happen more quickly, and anything that reduces false alarm rate in a gigafab can save a whole lot of money and pay for a lot of software. All right, there's another, I talked about this status monitoring or throughput monitoring. The question of where does all the time go has classically been looked at from an equipment perspective, and that's what's driven the OEE standards, E10 and others. If you have sufficient information from the equipment and a little bit of supplemental information from other systems, you can actually take the 6 standard OEE states and break them into even finer grain states that give you a better idea of what happened within those 6 states. So again, this all depends on additional information that allows you to subdivide the standard 6 states into deeper ones. The dual, if you will, of this time analysis from the equipment perspective is looking at it from the product perspective. So, where did all the time go if I'm looking at it from a lot or a substrate perspective? And the two together give you a powerful way of analyzing productivity and cycle time, both at the equipment and the factory level. Now, the semi-standard that actually defines all of these things is E168, stands for Product Time Measurement, and it was originally fostered as a program called Wait Time Waste. And the idea was, if we know where material is waiting in a factory, either in a factory or in a piece of equipment, we can look at those and see if we can squeeze out some of that time. And what you need, of course, is very granular events within the equipment to do that. And you need to have a way of defining those time elements in according to a standard. And so each of these blue, green, and yellow bars here, and the red one, actually have semi-standard definitions and standard events that bracket their start and stop. So this is a standard that was actually well ahead of its time, because you had to do a lot of GEM event data collection to support it, which is now much easier to do with the EDA standard. So using E90, E40, E87, and E157 events, you can do a very fine-grained job of knowing exactly where every FOUP and every wafer spends its time in the factory, and then go through a process of actually looking at those both waiting time elements and the active time elements, seeing where you can cut out unnecessary delay and save cycle time there. So again, the EDA leverage on this particular application is all of the tracking events that tell you exactly what happened to a piece of material and what it was waiting on or actively doing at a time. All right, another application, of course, so we don't want to forget the subfab people. Subfab equipment has a variety of custom interfaces. The pumps, abatement systems, chillers, all that stuff that people sort of took for granted for a while is now becoming more important in process behavior. That's especially true of the dry pumps that, if unattended, can end up with backflow problems and, spoiling a process. And so monitoring that information in real time is now becoming more and more important. A lot of them have had gateways to, let's say, to a database that you could look at issues after the fact, but being able to look at this in real time, blend that data into your fault detection application, is to know if the combination of what's on the fab floor and underneath the floor is working properly is becoming more important. And so what you will see is gateways that recast the information from those subfab components into an EDA standard, so that data can be blended into data collected from the process equipment in a seamless kind of way. Again, that doesn't happen magically. There's some system engineering that has to go on, but from an application standpoint, being able to consider all that together with in a seamless way is an innovative approach to this. And so this is typically the domain of the facilities folks, which haven't gotten classically a lot of attention, but it's now becoming more and more important. Okay, the last one I'll touch on is machine learning and AI applications. You're starting to see, of course, more and more of this kind of information, and in addition to the sort of online applications that keep a factory running, the process control, scheduling, dispatching, SPC, all those things, people are collecting massive amounts of data to develop predictive models for manufacturing behavior. And of course, the principal source of useful information for those is the equipment itself. And so having a way of tapping into the equipment in real time, collecting that data, storing it, and then providing that into the machine learning libraries is becoming a key use of the EDA standards. Of course, data collection is only a piece of that problem. You need to be able to transform that and put that into there's a lot of data wrangling that goes on in this domain. To put that into sort of cloud-based systems or other places that these machine learning technologies reside. So But again, the key enabling piece here is access to the equipment data. And the ROI factors affected by this particular domain are plenty. So, okay, let's shift gears again now. I had a longer list of applications that can be affected. If you're curious about any of those, please contact us. But I just wanted to give you an idea of how the EDA standards are leveraged for many different stakeholder types to support manufacturing. All right, one of the slides that Jack would have covered if he had been available was the importance of getting your specs right, because the EDA standards themselves, although they do specify the components of a model and the access methods to that model, and even some of the structural information requirements of the equipment model, they're silent on many of the details. They're also silent on the specific performance requirements. There is an expectation that the EDA standards would support much higher performance and higher granularity data access, but that's not actually written down anywhere. And so it's important to put those specific requirements and expectations into a purchase spec. Otherwise, somebody could deliver a perfectly compliant piece of equipment that had a useless model and slow data collection that wouldn't support the kind of applications we just went through. And so getting the purchase specs right is an important process, and making sure that the affected stakeholders, some of which I mentioned in the previous segment, are involved. And so we've developed a process for doing this that I'll cover here briefly. So I think actually, yeah, a key point to make, we've got another survey question coming up, but a key point to make here is that in order to run your factories, there are a number of KPIs, depending on the operational type of the factory, that are important. And what typically drive those KPIs are manufacturing applications that collect and use data and that can then be managed. That data, of course, in an EDA context is dictated, the available data is dictated by what's in that model, but the model is developed from the tool supplier side. So even though the requirements come from right to left on this picture, the actual implementation of the model comes from left to right. And so it's important to make sure that the specification includes what you expect in that model and the performance that you expect. Otherwise, you may not be able to achieve those KPIs. So I think we do have, yes, here we go. We do have a second poll question here. So we'll pause while people address that. And again, we at Symmetrics, because most of our customers are tool suppliers that are implementing either GEM 300 or the EDA standards, they of course get requirement specs from their customers that they have to address. And so we've seen most of those in the industry. We know what those requirements are, and we can actually help you on the factory side develop good versions of those for yourselves so that you get what you expect when the tool purchase comes along. So let me pause here for a second while people are answering that. If that process sounds interesting to you, please contact us. We'll definitely help you understand how we could go through a stakeholder review here. Well, let's see here. Yeah, a number of folks have actually tweaked their specs in the last half of them in the last year or so. Some in the last 2 to 4, and some not for quite some time. So, for those of you in the 2 to 4 or even the 5+ category, if you'd like some help with that process, just let us know. All right. Moving ahead. Yes, well, again, we have a process for doing that. EDA purchase specs cover a broad spectrum from sort of at the left-hand side, 3 pages of, here's the list of standards we want, E120, 25, et cetera, with maybe some, a little bit of additional information. We see bigger specs also, but frequently they're just cobbled together collections of material from old Semitech presentations or excerpts of the semi-standards themselves. A good purchase spec doesn't actually need to repeat any of the information that's in those standards because they're actually very detailed and well designed themselves. What you really need is a spec that describes how you intend to use that standard in your factory. And that means making sure that your expectations for performance, for visibility into equipment behavior as dictated by the model, built-in capabilities that you might expect to see, built-in data collection plans that support monitoring of frequent conditions or failure modes that the tool supplier understands. Testing and acceptance criteria. This is one that the semi-standards are completely silent on, but there's a lot of information available about how to reliably check these equipment to make sure they follow the standards. So our goal would be to help create one of those specs on the right-hand side. The way we go about that, of course, is by interviewing your different stakeholders, and we have a questionnaire designed specifically to do that. And one of the areas, of course, that's most important is the model content requirements. And you may ask the question, well, what do I need in a model that's not already specified by the standard? Well, some of those examples are here. In a purchase spec, you may or may not have sections that are specific to a given process, but your fault detection and control people do have probably process-specific parameters that they want access to in order to do the kind of control model development that they have to do. Also, the operating mechanisms that maintain that control, some of those are at a level of detail below what's typically seen in the GEM interface. But if you're trying to do fingerprinting and watching for problems before they occur, you may want those sort of PID control parameters for the underlying mechanisms of RF control or vacuum control or flow control. These things that all go together to make up the process behavior. I mentioned already built-in DCPs. The EDA standards actually account for a thing called a built-in DCP that the tool supplier can provide that is not deletable, that can be in place for monitoring common failure modes. These are typically done for field service applications by the suppliers themselves, but you as an end user could require additional DCPs for the things that the tool supplier knows about, rather than discovering all that yourself. Of course, tool and platform performance parameters, these can be put in as actual model contents as well. Countdown timers and events for lot completion for processes for which that's important. Making sure that all the field replaceable units have explicit nodes in the model so you can monitor their behavior and their status. And then finally, the other stakeholder use cases that are mentioned across the board here, you want to make sure that they all have the data they need to support applications that then drive those KPIs. So again, we have a lot of experience in different application areas that drive model and interface content that should be in your purchase specs. So what might that look like when you're all done? Here's kind of oops, went ahead. Here's a picture of what the major sections of a purchase spec. Of course, you're going to want references to the standards required, not just semi-standards, but other software and integration standards. You'll probably also want to specify something about the the execution platform that is running in the equipment. For example, you don't really want an EDA interface shared with a maintenance database or other control software, because you don't want data collection to impact tool performance or vice versa. You could then have sections which augment or clarify the specific standards that are referenced. So again, model content and performance and built-in capabilities. These are all additional information that you would go above and beyond what's referenced in the standard. Model content by process and use case. Performance and data quality. Again, since the standard is silent on these areas, making this explicit, and making it explicit not just in terms of total bandwidth required, but actually putting in your spec the kind of data collection architecture you expect. So, you know, how many chambers might you be collecting information from simultaneously? How big might those data collection reports need to be? What range of frequencies will you need for different parameter types? You know, what is the sampling rate? Are you sampling rapidly, changing parameters fast enough to actually catch those differences? So putting this in your spec is important. And then finally, pre and post delivery acceptance testing. So these are the kind of things that should go into a purchase spec, and the result would be, you know, a spec like that with a consistently formatted checklist that would make it easy for the suppliers to respond and for the purchasing people to evaluate that response. All right, the final piece I wanted to address is, you know, where all this stands. If you'd asked the question 7 or 8 years ago, well, this all sounds great, but who's using these standards? You know, where can I find equipment that implement them? The answer would have been, hey, you're on the early adopter phase. Happily, though, I can say that right now, the major chip companies in the world are sort of all in the camp here. And so, starting with our friends at Global Foundries, our AMD at the time, way back in 2005, Toshiba was also an early adopter, and then the Taiwan foundries came on board, and then you can see the knee of the curve here kicks up when, you know, Samsung and Hynix really got involved in the standard. So right about that period, we went from general availability of Freeze 1, which was the first generation of the EDA standards, into the availability of Freeze 2 and the E164 model content standards. This captured a lot of the best practices from these early adopters into the next generation of standards, which is now pretty much generally available across the spectrum of process equipment. So frequently we get the question too, well, you know, can I buy a piece of equipment for all my processes that include these standards? And the answer now is yes. Not all tool suppliers have them, and not all tool suppliers have the latest generation, but most are working in that direction. And again, just to sort of summarize the motivations from the factory side that I've covered already, but, you know, process visibility, better application performance based on availability of data, you know, higher speed and better quality data collection, the easy integration of disparate data sources for those devices beyond the tools themselves, flexibility to support changing requirements by having DCPs come and go as they need to, and of course the factory software engineering efficiency that's enabled by having easy, flexible access to the data. So the sort of best practices are using the latest generation of those standards to get the information needed for those factors. Okay, the final piece here is what's going to happen this time next week. And we have covered a lot of the what and why. Next week, we'll actually be talking, the title of the webinar is Harnessing the Power of SEMI's EDA Standards Implementation Best Practices. And that webinar will complement what we've discussed today with information about how these things can actually be implemented. Our focus will mostly be on the factory side. So we'll be talking about technology trends that drive factory system architectures, again, the kind of edge devices that may be the data sources, above and beyond just equipment itself, the sort of cloud native platform architectures that are now in place to capture and use that data, the sort of .NET 5 strategies people are employing to open up the range of system possibilities for implementing the sort of platforms and ecosystems available now, open AI and machine learning libraries. Again, it's a new world out there. So we'll be talking about that. We'll also be talking about how those technologies can be used to meet a sort of gigafactory performance, reliability, and scalability requirements. But knowing that you can never start from whole cloth, we'll talk about ways of enabling smooth migration from the current state of the world. And we'll also touch on some of the best practices for equipment suppliers because we have a lot of experience in their challenges as well. So this is what we'll cover this time next week. And we hope to see many of you and others in that webinar. Just to wrap up, we'll just make the point that semi-standards are what enable a lot of this picture to work. 2 summers ago, SEMI crossed the 1,000 standards boundary, and starting I guess 40 years ago, with the first standards for wafer size, it's now a massive initiative that enables these factories to run automated. And GEM and GEM 300 and EDA now combine to collect data and support the automated operation of these gigafactories, day in and day out. And so we appreciate your interest in this latest topic, and we'll turn it over now to our facilitator, Cheyenne, to deal with questions. Thank you.
Thank you, Alan. So we're now going to begin answering questions submitted during today's presentation. As a reminder, you can still submit questions through the question pane in your attendee control panel. And Alan, our first question is, our SexGEM data collection systems are stable and unlikely to change for a while. Can we use EDA on the new equipment without disturbing the environment?
Great question. And it's a shame that Jack wasn't here to present his architecture slide. It'll actually be in the packet that goes out, but in there you'll notice that the servers that connect to the EDA interfaces are actually separate from those that connect to the GEM and GEM 300 interfaces. And so since it's a different networking technology, you can actually add it incrementally, non-intrusively to a GEM data collection world without any negative impact. And so, you could of course start from scratch and embed GEM and EDA data collection into a single system, but that's not actually necessary. There are a variety of ways of doing it that can be very independent and allow you to migrate seamlessly. So EDA need have no impact whatsoever on the GEM data collection. Great question, thank you.
Thank you. Okay, next question. We see the adoption curve among chip companies. How well adopted are the EDA standards across the equipment supplier community?
Another one, actually, that we get a lot. That picture changes so often that I didn't bother to do a slide with it. But at this time, you can actually get EDA interfaces on every type of process equipment that you would need in a modern gigafab, and even on some instances of metrology equipment. I mean, metrology is a special animal because a lot of the data is not your typical process and equipment events and parameters. It really has more to do with the characteristics of the material itself, the wafers themselves. But some metrology suppliers are actually putting EDA interfaces on because they are complex pieces of equipment on which you do fault detection kind of applications. And so, but every process type certainly now has available EDA interfaces, and if not Freeze 2 at the moment, will be soon.
Thank you. So how adapted are the EDA standards to the back end? For example, probing test and final test.
Oh, another good one. The standards themselves are certainly applicable there. The components of the metadata model for a back-end equipment would be very different. I mean, you'll still have events, parameters, and exceptions, but the way they are grouped into nodes and modules would be different. The control systems of back-end equipment are typically different as well, and may not have as easy a place to drop an EDA interface on. And so, the back end is now just now at the point of starting to implement more and more fault detection and real-time sort of throughput and behavior tracking. Certainly, if a new tool were being developed in a back end with a new control system, it would be a great thing to have an EDA interface. But I think where the industry is now is mostly starting to adopt the GEM 300 capabilities necessary for more automation and precise monitoring. EDA will come further down the road.
Thank you. And so how does this suite of standards compare to OPC UA?
Another good question. OPC UA is also a model-based approach. The difficulty with that, though, is OPC UA is really more of a specification of an architecture, not a specific implementation. So in order for two OPC UA systems to effectively communicate, they have to have adopted the same technology stack. And by technology stack, I mean the lowest level of communication paradigm, which would be TCP/IP in most cases. But then there are XML and binary alternatives specified within OPC UA. You go up a level, you have different profiles that you can apply with different model structures. And so some of the same capabilities in the EDA, again, knowing where in an OPC UA model to start the query and upload the model, those exist, but it's not as interoperable out of the box unless those two components have been designed together, are done with the same technology stack in mind. So they share some similar characteristics, but not, there's a lot more that has to be specified for two OPC UA components to effectively communicate.
Thank you. And I know that we're running short on time, but I just want to try to squeeze one more question in here. Is the EDA built top of GEM 300, or is it completely independent standard?
Excellent question. It's an independent standard. In fact, one of the guidelines in E164 says that EDA should not be implemented as a protocol translator on top of a GEM interface. The key to its performance and visibility should be direct access to the data sources within the equipment control system rather than being a layered architecture. And so in order to support that performance, it really needs to be independent. So some early implementations didn't necessarily follow that, and it wasn't a good scenario. But yes, an EDA interface should be a native direct access to the data sources and not a layered approach. And it was. Now, E164 does specify that anything available through the GEM interface should also be available and share the same identical timestamps through the EDA interface. But after that, the two should be separate.
Great. Well, thank you, Alan, for presenting today, and thank you everyone for attending today's webinar. Semi-EDA standards are essential for smart manufacturing, what you need to know and why. If you have any other questions, please email them to marketingmanager at symmetrics.com. Once you leave today's webinar, you'll receive a survey on the presentation, and we would appreciate it if you could complete that and provide your feedback. You will also receive a follow-up email within 48 hours with a link to view the recording of today's webinar. On behalf of Symmetrics and our guest speaker, thank you for joining us today and have a great rest of your day.
Thanks very much.